We have utilized it in Coastal Act project to improve nearshore wave search modeling during severe events. And this was a collaboration between us as NCEP, US Army Corps of Engineers, and other partners at NOAA. And of course, we require two inputs from atmospheric storm surge models from NCEP and NOAA. So it's a collaborative work between lots of people and institutions. Okay, so here is the outline of my talk, but first I would like to explain our requirement for nearshore applications like Coastal Act project and how WaveWatch 3 recent developments is addressing them. In order to have better prediction of total water level in coastal regions, we do need a fully coupled system of wave surge and riverine models. We also require each individual models to be fast and accurate enough. For the sake of validation, we also need to have observations in impacted area, over land and in nearshore. And also we need to improve the physics inside the model so we can have better representation of the physics and nearshore hydrodynamic. So WaveWatch 3 is one component of this couplet system, and we had a couplet of challenges in front of ourselves. First of all, we needed to go very high resolution to resolve nearshore physics. And let's say at a street level like 30-meter resolution, which means that the grid for the entire, for example, East Coast for tropical cyclone would be very large to cover the entire area. And also it should run as fast as other components like AdCirc and National Water Model. And as you know, traditionally spectral wave models are slower than surge models. So we need to allocate more CPUs to this model or improve the speed of the code. Also, once we resolve nearshore geometries with a high resolution grid, the pre-existing physics in the model might not be accurate enough. So we needed to retune and also improve the physics, pre-existing ones, and also probably we need to introduce new physics in the model. So I will go over each of these aforementioned targets, improvement in efficiency, better physics, and then I will show you some validation studies in lab and also real case application for Hurricane Irma and Florence. And then I will show you that with all of these improvement in the WaveWatch 3 model, we are now able to run WaveWatch 3 on ensembles, efficiently, and we can provide some uncertainty analysis on the wave output due to errors in the atmospheric model or in the wave model. So before I jump to the model and case studies, I also would like to show you how we maintain the code on GitHub. As a part of EMC mission, all of the model workflows and operational implementations should be aligned to open source development paradigm concept. So GitHub is the infrastructure that NCEP has chosen, and WaveWatch 3 was the first model across EMC that moved to GitHub in 2019. The code is publicly available to users, and we maintain a wiki page on the upper right-hand side, and also we have a mailing list for the users. We also have international partners, including Infirmary in France and UK Met Office and US Army Corps of Engineers, who help us to improve the model and grow the community development. We have regular development meetings and user meetings every few months and annual wave summer school at UMD, except this year due to the COVID incident. And then if you are interested, you can join our family, and you are more than welcome to communicate with us and then see what we are doing. And if you have something to present, you are more than welcome to attend and present your work in our developer and user meetings. So now let's talk about the model development. I will go through each of the pieces, and then the details can be found in these two publications, one recently published in Coastal Engineering and the other one is the WaveWatch 3 manual. Going back to WaveWatch 3 initial design by Henrik, its main purpose was global wave forecasting on a structured grid, and at the time it was equipped with a novel and efficient parallelization algorithm called CARDEC or mosaic approach. It was good enough at the time for that purpose, and even later when the multi-grid capability added to the model, it was good. The operational multi-band setup, including a couple of structured grid with different resolutions shown on the left-hand side. And if you notice, for the model and parallelization, this approach was the only approach that WaveWatch 3 is equipped with. And almost 10 years ago, WaveWatch 3 was adopted to unstructured grid by Professor Abdolali and Aaron Roland. And the old polarization algorithm was still used by the model for this. But there was some limits, like the number of grids, so we couldn't go beyond 2 million unstructured nodes. And then the scheme on the structure on a structured grid was still explicit, so we had some limitation in terms of current number and CFL constraint. So the problem arises when we wanted to go higher resolution, which means that we need to have a larger grid, and then we need to use more CPUs if we want to do, but the wave model had some limitations. So all of them led to some slowdown in the model, which was not appropriate for our purpose. So for this reason, we implemented a new polarization algorithm as shown in the upper right panel. This algorithm is based on parametric libraries, which is well proved in other models like AdCirc and FBCom, and we also introduced an implicit numerical solver to avoid CFL constraint in the explicit scheme. Here is a schematic view of the different polarization algorithm in our East Coast mesh. The upper left one is a regular grid with 10 kilometer resolution almost. We had used just Kardec approach because it was the only option for this grid. And then as you can see in the schematic distribution of the computational, on the grid nodes to the computational nodes, you can see the nodes are distributed on allocated computational cores in order, in this case on 720 nodes. So you see it has a very beautiful shape. In the upper right-hand side, we use the same algorithm on an unstructured grid. It's a 1.8 million grid, HSOFS, and as you can see, the grid nodes are not distributed based on, they are distributed based on their index on the computational cores, so it looks like some kind of random shape. And in the lower panels, we have used the domain decomposition, the new algorithm that we have implemented, using Metis and parametric libraries on two unstructured grids. One on the left is the 250,000 node, and the other one is 1.8 million. And as you can see, the domain is decomposed into subdomains, and each computational core takes care of each domain and talk to neighbors during computations. The same approach is implemented in other models like AdCirc and FBCom, as I mentioned. Okay. So here you can see the performance of the model before and after the implementation of the new parallelization and implicit numerical solver. The vertical line is showing the limit of the model in the past, around 1, which was the upper limit of the number of CPUs that we could allocate. And as you can see, after this new implementation, there is no limit, so you can allocate any number of CPUs as available to your model and do the computation. We also check the performance of the model on different schemes and different grid resolutions to see which approach is more appropriate for different applications. So users can take a look at this graph and choose what approach is best for them to have an efficient computation. And as you can see, we have speeded up, and then we could reach about 2 orders of magnitude faster model relative to the real-time simulation. So, and the animation that you have seen on the left-hand side was a Hurricane Ike simulation on a 9 million grid with 10-meter resolution on 2,000 CPUs on our HPC at NO. Okay, so the model is equipped with a powerful parallelization algorithm and numerical solver, the implicit one. So we can go very high resolution on very large grid, and now we need to think about nearshore physics, which previously was not possible to investigate. So one of the source terms we have implemented in interaction of the WaveWatch tree, in the WaveWatch tree was interaction of the waves with vegetation, which was not in the wave model before. Also, we had some, this vegetation interaction is very important in wetlands, and these days it's a growing concern in all the communities. So I will show you some lab cases and validation in the coming slides. Okay, so the source term followed the Dalrymple 1984 paper who introduced the dissipation through rigid vegetations in the conservation of the energy flux equation, and then they consider that the dissipation is just due to the drag force, and then they express it in a Morrison type equation. And as I said earlier, early formulation focused on monochromatic waves and approximated vegetation as an array of rigid vertical cylinders. It was later extended for random waves transformation over mildly slope flexible vegetation field, which was introduced by Mendes and Losada in 2004. So after implementation of the source stem, WaveWatch 3 has two options, one for homogeneous vegetation field, which is good for the lab cases, and the other one is for temporal and spatially variable vegetation field, which is good for seasonal computations or seeing the effect in wetlands with different vegetation coverage. So users can have lab cases or real case applications, depends on their observations. Okay, so here you can see the validation in a lab case. So we validated our implemented vegetation source stem for 63 sets of laboratory cases with homogeneous vegetation field conducted by Anderson and Smith in Vicksburg, Mississippi. And you can see the dimension of the flume, 42 meter, and 3 different water depth, and I think 3 different wave period, and different vegetation density and height. So here is, I just showed 3 of them, 3 samples. The 2 first one are single peaked, and the third one on the middle panel on the lowest sub panel, it's the double peaked wave, double peaked spectrum. So you can see the results of the model for different vegetation density, 0 vegetation or density of 200 stems per square meter or 400. And you can see the observations with solid line and model results with dashed line. And as you can see, we tune the model to, I mean, in terms of the drag coefficients, we tune the model to capture all of the dissipation properly. And so you can see these are, and then we had 60 more lab cases that we have validated the model against, and all of them were good. So let's move to a real case application, Magoti Bay, located in Chesapeake Bay. So in these real case applications, in collaboration with George Mason University and Celso Ferrara and Arsalan Khalid at George Mason, this group have been conducting lots of field works. They observed multiple sites during normal and severe events, and you can see their sites on the left, and on the right, the attenuation of the wave over vegetation during Hurricane Joaquin in 2015. So obviously, prior to each event, they usually collected lots of information about the vegetation coverage, and then they put the instruments, and after that, they also conducted some measurements to make sure everything is collected. So here you can see you can see the location of our test study, Magoti Bay, at the top of the bay, where we can study the effect of swell and young waves together with vegetation map on the right. And then you can see the location of observations along a transect, 2 transects during different deployments. It shows on the lower panels. So as you can see in this slide, they did the observation in different seasons. So we aim to study the seasonal changes effect on the dissipation by vegetation. And as you can see, in winter or fall and summer, the vegetation coverage is totally different. As I mentioned earlier, we implemented the special temporal variable vegetation field. So we can introduce them in WaveWatch 3. And then since we had the wave gauges and also water level gauges at the same locations on those transects, we could run AdCirc model, validate the AdCirc model, and also we ran WaveWatch 3 model and compare the results at those gauges, and we had some very good results based on our study. So here, the transect 2, as you can see, for validation of the AdCirc and WaveWatch 3 model, we had a grid with 5 meter resolution in Magoti Bay, but it was covering all of the entire East Coast, and I think that the size of the grid was about 700K nodes, but the concentration was in Magoti Bay with 5 meter resolution, which is a wetland, and we needed to resolve the channels in that area. So we put the gauges were located in wet to overland gauges from top to bottom in this plot. And in each subplot, you can see the water level is shown by black and model outputs are red. And for the wave side, the blue is the observations, significant wave height, and then the magenta is vegetation, vital vegetation, WaveWatch 3, and then the green line is the vegetation. So we need to tune the CD compared to do the observation to tune it, but as you can see, we can see the effect of vegetation on the dissipation of the waves. And we are moving to the other transect 3. We had the same story, And I think I forgot to mention the forcing came from HWARF model, which is our hurricane WARF model with very high resolution moving nested grid for these applications. And we had that capability to impose very high resolution reinforcing to our model at Silicon WaveWatch. So here, another system that we have implemented, we revisited the already implemented depth breaking and triad interaction systems and adopted them to the new implicit solver. We debugged them and added some limiters, and then we retuned them. Also, we validated them against a well-known laboratory case, Booj 1996 in Netherlands, and we added that as a regression test, a standard regression test in our public repo. And due to the implementation of a new boundary condition type, Neumann boundary condition, we could make our grid much, much narrower like a flume, and then we don't need to spend lots of computational time to expand our grid laterally to have the effect of all of the things. So this Neumann boundary condition is implemented for our lab cases and also for nearshore applications like at Duck, North Carolina with Army Corps of Engineers. And then I think I need to move faster to second one. Okay, so the largest scale application within Coastal Lake project, we ran WaveWatch 3 and AdScript model for different hurricane scenarios like Isabel 2003, Ike 2008, Sandy 2012, Irma 2017, and Florence 2018. For the sake of time, I just show you Hurricane Irma and Florence, but we have a publication on Ike, and also for Sandy and Isabel, another publication just recently published in JGR by Office of Water Prediction folks about Sandy, Isabel, and Irene. Okay, so let's start with Hurricane Irma in September 2017. In this plot, you can see the observations during Irma, NDBC and satellite track for offshore validation, and USGS quick deployed gauges on land. And in this specific case, they put the gauges on eastern side of the Florida Peninsula. The model grid was the HSOFS grid, 1.8 million grid with 200 meter resolution grid, but we aim to improve that to 30 meter. We tested the model on 120 meter coastal resolution, but our aim is moving to 30 meter resolution at S3 level. So in this slide, you can see the HWARF model, which provides us the atmospheric forcing for all of the downstream model. WaveWatch 3 obviously requires just the wind speed at 10 meter, and AdScript model requires pressure at mean sea level and also wind speed. But for so here I just showed the wind speed at 10 meter resolution with some zooming window in Florida Peninsula, and on the right hand side you can see the wave output in terms of significant wave height, and in the lower panel you can see the zooming window. So as I said, since we had a faster WaveWatch 3 and also we had HWARF with the operational HWARF with for the ensemble members, we could do some statistical analysis on the spread of the model error, and with use of those information we generated for the ensemble members to force the downstream model, in this case WaveWatch 3. And since, as I said, WaveWatch 3 was very fast, we could run the multiple ensemble easily and then perform the statistical analysis to realize what was the error just due to propagation of the error from upstream model, the atmospheric model, to the downstream model. So as you can see, in all of these subplots, on the left, the significant wave height and wind speed is shown at different NDBC location. The middle panel is the peak period, and on the right-hand side, that's the wave direction. And all of those ensemble results are shown in gray. The deterministic one is blue, and then the observation which falls within all the spread of the ensembles are in magenta for the wave and in black for the wind. And here, taking advantage of all of this ensemble modeling, we can evaluate the uncertainties in the model at locations with observations like previous slides or across the entire domain where we don't have any observations. And then based on those things, we can evaluate the uncertainty and error. And I think here in the upper panel, you see this, the snapshots of the wind field close to the landfall and the mean of the model ensembles. And then in the lower plots, you can see the standard deviation of the wind speed. We had a paper just published in Atmosphere. It was accepted last night. And then it's about all of the improvement in the HBARF model. And then we had another paper submitted to Ocean Dynamics about the uncertainty analysis of the HBARF model and WaveWatch stream model based on all of the information I provided you. So for more detail, you can check those papers, or I can share the draft of this paper under review with all of you. So in this plot, that's the same story. The upper plots are the significant wave height, the mean of the ensembles, and then the lower panels, that's the standard deviation. So these are very useful for uncertainty analysis. And then we use the ensemble modeling to evaluate what error propagated from upstream model to the downstream model. Move to the Hurricane Florence in 2018. We had, again, satellite observations, NVBC observations, and also USGS deployed lots of pressure gauges with 4 Hz resolution, with 4 Hz sampling frequency over land. So we use all of these to validate our model. So here again on the right-hand side, that's the wind speed and a zooming window in North Carolina where the landfall took place. And then on the left, that's a significant wave height and then the zooming window in North Carolina. Note that we use this time HBARF model plus hair because HBARF model was not able to go beyond the landfall time, and then from there we merged the hair output with 3 kilometer resolution to HBARF, and then we continued the simulation. So here I just showed one of the validation sites, the NDBC, and on the left-hand side the validation for the atmospheric model and wave model at NDBC buoy. Here, okay, so for the gauge 41013 near the landfall and on the continental shelf, I showed on the left-hand side the atmospheric model wind speed and wind direction with overestimation of the HBARF, which is a non-problem with Hurricane WRF model. And in the middle panel, the significant wave height, the peak period and wave direction from the observation, and also 2 different grids. One with 200 meter resolution, coastal resolution, and the other one is with 120 meter resolution with 4 million nodes. So obviously there is no significant difference at this location because the mesh resolution at this location was almost close to each other. But where we move to the landfall and nearshore and overland, the differences are showing. Okay, so here in collaboration with USGS, we use quick deployed gauges which are mostly overland for inundation and overland validation. Here on the left, the gauge bracket and coordinate are shown. And in the middle, the spectral density plots from the pressure gauges data and the model results from 2 simulations on 200 and 120 meter coastal resolutions are shown. And on the right-hand side, the wave height, peak period, and direction. And in the lower panel, the water level from the observations and at-sea model. So we need to do lots of improvement in physics, and also we need to improve the coastal resolution to 30 meter to capture all of the changes in geometry. With 200 meter resolution, obviously, we could not represent all of these changes in the geometry, and that's why we still lack lots of, we see lots of differences in the model and observations. So in terms of wave search coupling, and in order to address one of the good points that Henrik mentioned in the previous talk about wave search and hydrological model coupling, within Coastal project, we are doing that. And then in other project in Alaska, we are also trying to couple wave model, search model, and sea ice model all together to couple and work dynamically together. And all of these are collaboration between different institutions. And I'm aware that people from, for example, University of Rhode Island and also Stevens Institute of Technology, they are also trying to utilize these developed coupling frameworks for their applications. So our design is shown in this diagram where the atmospheric model suite, including HWRF, HAIR, and WRF LES, are connected to the system in a one-way fashion, which in this atmospheric models provide wind and pressure to the surge model and wind speed to the wave model and 7 other variables to national weather model, the hydrological model. And then from the surge side, the water level and current are advertised from the surge model to the wave model as an input. And on the other side of the system, breaking waves transfer their momentum to the ocean currents And in our coupling system, the wave model provides wave radiation stress gradient as a source term to the surge model as an additional depth integrated stresses to the surge model. And then all of them are coupled and running together. And right now we have implemented wave model, WAVEWATCH and ADSIC model fully coupled, and we are at the stage of the testing, tuning, and also optimization of the coupled system. And then with our colleagues at Office of Weather Prediction, Water Prediction, we are trying to couple the national water model to the system. So right now, I think in the paper that just it's impressing JGR, we have shown the concept for the coupling with hydrological model in a one-way fashion, and then we are working on that with our colleagues closely with Trey and his team to implement the fully coupled system with their model. So here I show the significant wave height for Hurricane Ike, the whole domain, HSOFS grid again, and then a zoom in window in Galveston Bay. And here you can see we have chosen this system because we had some measurements in 10 meter in surf zone collected by Andrew Kennedy from University of Notre Dame. And so we picked this system and we conducted the simulation for that. And on the left-hand side, the HS is shown with a zoom in Galveston area. And then we ran the standalone wave model. And then if you look at the delta, it means that the difference between fully coupled model minus the standalone wave model, and you can see how significant the difference is. Most of it's because we had wetting and drying and tidal oscillation in the surge model, which is introduced to the wave model, and on the other side, the radiation stress from the wave model to the ADSIC model. So here you can see the maximum absolute value between the fully coupled and the standalone runs. And then at the observations at those gauges on 10 meter water depth on the west and east side of the landfall in the lower left panel UV, WX, YZ gauges. One of them is on the top of the hurricane track. You can see we had lots of improvement from standalone to fully coupled. We published it in Journal of Marine Science and Engineering with some justification why we missed the forerunner due to the Ekman setup, referring previous studies in that case. And also we are showing that we need to go higher resolution. So this under development work and optimization is underway. So in conclusion, as I said, the WAVEWATCH on unstructured grid is now using the domain decomposition algorithm. And since most of the initial development for WAVEWATCH was based on explicit scheme and most of the arrays were globally advertised, now we move them, all of them locally advertised. So it means that each CPU is just taking care of its allocated nodes in the grid. It doesn't care about the rest of the things and just communicate with others. So it makes the code much faster. Also, we have shown that the concept is working within HPC environment, and then we could run fully coupled wave search system for different hurricane scenarios, and all of them are compatible with NOAPC and ESMF regulations. And then with the nearshore physics implementation, like vegetation, SORSEM, or adapted triad and depth breaking, we are moving to have better representation of the nearshore physics. And then we showed some laboratory cases and also large-scale applications, ensemble modeling. All of these are shown, and they are all showing that we had some great improvement in the model outputs. And as I mentioned, fully coupling, the national water model is coming to the game as a fully coupled system. But right now we have tested it one way, and we had lots of improvement just because of that one-way coupling. And here there are some references, and as on the left-hand side, this is the first global unstructured grid that I could run with WAVEWATCH with, I think, 5 million nodes with 6 kilometer minimum resolution in collaboration with people at University of Notre Dame, William Pringle and Johannes. And you can see before this implementation, it was not possible to run such a large grid. And now we are able to run models on any given grid as far as I had those those scripts, it's running well, and there's no problem with that. Thanks for your attention. I think that was the end of my presentation.
Thanks so much, Ali. That was a great presentation. So in interest of time, we've got about 3 minutes left. I got 2 quick questions I'll address in the chat while we switch back to my screen so I can wrap us up. And the first was Professor Chen said that his group is testing the unstructured grid in WaveWatch 3 with APOS and wants to know who he should contact in your group with some technical issues. So, Ali, would that be you that Professor Chen should reach out to with the technical issues?
Yeah, sure. Yeah.
Okay. So, my screen should be popping back up in just a moment, and Ali's email address is at the bottom of this slide. So, Chen, feel free to reach out.
Okay.
And then the question that came in is, are the changes scheduled for inclusion into specific WaveWatch 3 builds yet?
So which one? I don't see that.
I think this is in reference to some of the new physics.
Mm-hmm.
I don't know if that was scheduled to go into operations yet or if that's something you're still testing.
So this is Hendrik here. For as far as I understand, the only place that we're using this, at least in operations, is in the Great Lakes. And so the Great Lakes still has the explicit version of it. But it would be very likely that we would go to the implicit version for the Great Lakes just for cost saving.
Thank you, guys.